GPS, or global positioning systems, are very important in our everyday lives and are able to occur because of special relativity given to us by Albert Einstein. Special relativity postulates that all laws of physics are equally valid in all frames of reference moving at a uniform velocity. The theory has consequences on time dilation, mass energy equivalence, length contraction, and the photoelectric effect. Its two postulates are that the speed of light is constant and that everything else is relative to the observer. This gives us the opportunity to have the GPS because an observer on the ground sees the satellites in space in motion relative to them. Special relativity predicts that we should see their clocks ticking more slowly. Special relativity predicts that the onboard atomic clocks on the satellites should fall behind clocks on the ground by about 7 microseconds per day because of the slower ticking rate due to the time dilation effect of their relative motion. General relativity, also given to us by Albert Einstein, must also be accounted for in global positioning systems. General relativity is a unified description of gravity as space and time, or space-time. The curvature of spacetime is directly related to the energy and momentum of whatever matter and radiation are present. Because the satellites are high above Earth, the curvature of spacetime due to the Earth's mass is less than it is at the Earth's surface. A prediction of general relativity is that clocks closer to the massive object will seem to tick more slowly than those located farther away. As such, when viewed from the surface of the Earth, the clocks on the satellites appear to be ticking faster than identical clocks on the ground. A calculation using general relativity predicts that the clocks in each GPS satellite should get ahead of the ground-based clocks by 45 microseconds per day. The combination of these two relativistic effects means that the clocks on board each satellite should tick faster than identical clocks on the ground by about 38 microseconds per day. The first generation of global positioning systems was created by the Air Force in 1973. Its purpose was to find lost soldiers, as well as to determine the math in launching missiles from a mobile platform. GPS, as we know it, started in 1989 with the launch of the first two GPS satellites. The network opened completely to the public in the year 2000. The network we use is called Navstar, and it is paid for and operated by the U.S. Department of Defense. This is currently the only functioning GPS system, but Russia, China, and the European Union have systems that are currently in the developmental stage. A GPS satellite weighs approximately 2,000 pounds and is about 17 feet across, with the solar panels extended. Its transmitter power is a mere 50 watts or less. A GPS system is made of approximately 24 operational satellites that are in orbit over a 12-hour period, which means that each satellite orbits twice around the Earth per day, moving at a speed of 9,000 miles per hour at a height of 11,000 miles above the Earth's surface. There is always 6 or 7 GPS satellites visible to your receiver. 4 satellites always have a line of stability to your receiver at any given time. When it estimates the position of those 4 satellites, it can predict your location in 3 dimensions through a process called trilateration. The receiver gets information on the location of 4 of those satellites and the distance between the receiver and those satellites. Using those measurements, the receiver can point out where you are through the use of overlapping spheres. Not only does your GPS receiver need to know the position of the satellites, it also needs to know the exact time when the GPS satellites send information. Every satellite has a clock in it that is accurate to a billionth of a second. Every receiver has a clock that constantly resets itself to match the last time it received the time from the satellites. GPSs are so accurate in time that they are also used in other timing situations where time needs to be synchronized, such as stock exchanges. The accuracy of a position determined with GPS depends on the type of receiver. Most consumer GPS units have an accuracy of about plus or minus 10 meters. Other types of receivers use a method called differential GPS to obtain a much higher accuracy. DGPS requires an additional receiver fixed at a known location nearby. Observers made by the stationary receiver are used to correct positions recorded by the roving units, producing an accuracy greater than 1 meter. Along with stock exchanges, there are many other applications to GPS systems. One is agriculture. GPS-based applications in precision farming are being used for farm planning, field mapping, soil sampling, tractor guidance, and crop scouting. It also allows farmers to work in low visibility field conditions such as rain, dust, fog, or darkness. GPS also plays a large role in the environment, as data collection systems provide decision makers with descriptive information and accurate positional data about items that are spread across kilometers of terrain, all made possible by the GPS, special and general relativity, and Albert Einstein. An interesting comparison of the GPS is that of the TV. The GPS signals are transmitted at a power equivalent to a 50-watt domestic light bulb. Those signals have to pass through space and our atmosphere before reaching your receiver after a journey of about 11,000 miles. Compare that with a TV signal, transmitted from a large tower approximately 10 to 20 miles away at most, at a power level from anywhere to 5 to 10,000 watts. And compare the size of your TV's roof-mounted antenna with that of your GPS, often hidden inside the case itself. I wonder that it works as well as it does, and when the occasional hiccup occurs, you will at least understand the reasons why. GPS systems are so important they are currently being upgraded. The current satellites are called GPS-2 satellites and are accurate to about 10 meters with a lifespan of about 12 years. In the spring of 2014, GPS-2F satellites are being launched that will be more accurate as well as more efficient. By 2020, satellite Type 3s will be launched that will be accurate to an arm's length and to a fraction of a billionth of a second. GPS can be seen in aviation, marine technology, public safety, and disaster, recreation, surveying and mapping, military operatives, and the conventional finding your way around. Albert Einstein made all of this possible through his relativity postulates in the early 1900s. His theories have made such a tremendous impact on all walks of life through the use of GPS.